So the tree that we have learned suffers a problem of high variance. That is, the training and test predictions would vary to a great degree. Hence we use bagging, random forest, and boosting to address this problem and improve our prediction accuracy. These are part of ensemble modeling. Now, ensemble modeling is a powerful way to improve the performance of your model. It is the art of combining diverse set of learners, that is individual models, together to improve on the stability and predictive power of the model. So we apply ensemble learning over and above the various models that we have built. But before we learn about these methods, we need to understand a concept called bootstrapping. Bootstrapping is a resampling method in which we take multiple samples using the same data with replacement and then generate B-training datasets. So instead of collecting different samples, we generate multiple samples from a single sample. This process is called as bootstrapping. Now, bootstrapping is a generic method and it can be applied anywhere. Now, the first concept is bagging. Bagging uses the concept of bootstrapping and it is also a generic approach applied over different techniques. So let's see how bagging works. First, we will see for classification tree. So here we have our training data set. From it, we will take bagged samples, say B1, B2 up to Bn. Now from these bagged samples, we will create models as M1, M2 up to Mn. So once the models are ready, we will give all the models our test observations and make predictions as P1, P2 up to Pn. Then we'll take average vote across all the models to classify an observation to a particular class. And this will be our predicted class for that observation. So that is how we do bagging for classification tree. Now for regression tree, the process remains the same up to step 3. But here, instead of taking the average vote across all models to find our prediction, we will take the simple average to get the predicted value. And that is how bagging works for regression. Now moving on to the next part. So remember, we are using ensemble methods to reduce the bias, or in simple word, to improve the accuracy of our tree models. In bagging, we create multiple samples and find the predicted value. But we must also know how accurate this value is. So for this purpose, we use something called out-of-bag error. Let's say we have a training data with 100 observations. Now it is seen that on an average, each bag tree makes use of around 2/3 of the observations. The remaining 1/3 of the observation not used to fit a given bag tree are referred to as the out-of-bag observations. So these out-of-bag observations are fed to all the models which do not have these observations in their bootstrap sample. And then average vote if it is a classification problem, or simple mean if it is a regression problem is taken for each of the out-of-bag observations which are passed through different models as their prediction. Then we can compare this prediction with the actual observation and calculate the error. So for example, total 33 out-of-bag observations were there and we predicted 25 correctly. So out-of-bag error would be 1 minus 25 divided by 33. So that is how out-of-bag error is calculated. Next we have VIF, which is variable importance factor. Now VIF tells us which variable is important by using RSS for regression and Gini index for classification. VIF is a score, and higher the score, then higher would be the importance of the variable. So that is how we assess the importance of the variable. Now there are certain issues with bagging as well. So predictions for bag trees suffer from a problem of correlation. Now don't ask me how. Let's just assume that it is proven by some intelligent people already. So we will just take it as it is. So what we did in bagging, we averaged the prediction over a large number of trees. But this does not help us overcome the correlation issue, and also does not provide a substantial reduction in variance. Now what we can do is, we can increase the bootstrap sample size to address it to some extent. Or else we can use another method called random forest to address this problem of correlation. So instead of using all the predictors, what random forest does is it uses k predictors out of the m predictors for building the tree. Then we repeatedly build trees by randomly selecting k predictors until we build n trees predefined by us. You can think of this as decorrelating the trees and reducing the variance of our prediction. So that is how random forest works. Now if k is equal to n, then random forest becomes bagging. Then the last technique is boosting. It also works similar to bagging. In boosting, the trees are grown sequentially. That means each tree is grown using the information from the previous tree. So it basically learns from the previous information, hence also called as converting a weak learner to a strong learner. Now boosting does not involve bootstrapping. Instead, each tree is fed as a modified version of the original dataset. Also, there are different types of boosting algorithms like AdaBoost, which is called adaptive boosting, gradient T boosting, XGBoost, etc. So there are pros and cons of each of these algorithms, but we will not go into the details of it. Let us just restrict ourselves to know the important details that are required to implement boosting. So there are basically three tuning parameters that should be our focus. First is the number of trees, that is B, which means how many trees we would want. Now unlike bagging and random forest, boosting can overfit if B is too large. Thus we use cross-validation to select B. Now we are seeing this term cross-validation over and over. Don't worry, we'll learn this in the later part of this module. We have a complete section dedicated to cross-validation. For now, just understand that it is used for selecting the best parameter or the best model. Then the second parameter is shrinkage parameter, that is denoted by lambda. This controls the rate at which boosting learns. It is a small positive number that ranges from 0.01 to 0.001. Now the choice of lambda depends on the problem. Small value may require large B for good performance and vice versa. Third parameter is the number of splits, that is denoted by D. It is also called as interaction depth. It controls the complexity of the boosted ensemble. Usually D is equal to 1 works well. Now these tuning parameters are something that you can learn over time. But there are certain basic directions that I have already explained here that can be used for selecting these parameters. So these were the three parameters that are required for us to implement boosting.